Yeah, so this is a talk that I'm going to do. It's like a kind of Babby proof of the FTC. Um, my name is Sai Sivakumar. Most of you know me as Metal, but because I want to keep this, I want to write this down as something I did. I'm going to use my name and face this time. Yeah. So let me begin with the outline. So we're going to talk briefly about Riemann integrals. And then we're going to actually state the theorem and then prove it mostly. There are some parts I'm going to leave out. I'll tell you which parts I'm not going to do justice to. And then just some closing remarks if I have any, if I think of anything interesting to say. Yeah, so Riemann integrals. So the reason I want to talk about this is because like a lot of the times in like high school or whenever you first learn calculus, it's like you learn Riemann integration, but then it's like after you learn the fundamental theorem of calculus, it's like you no longer need to know this or something. You just kind of spam, antiderivatives wherever you want and get, the integrals that you want. But I think it's important to say something about this, even though it's a little confusing for me since I haven't actually taken real analysis. I don't like fully understand the conditions and stuff. But yeah. So we want functions from closed interval AB to the real numbers to be bounded. So I don't want something to go like off to infinity in either direction in this interval. And it can be piecewise continuous, but I say almost everywhere because you can have some like removable discontinuity or like a jump discontinuity or whatever. You can have a few of those, but not like, I guess, an absurd amount. I'm not really sure how many constitutes like a really, really bad amount, but this is what I read. So I'm going to list a few examples of some problems that come up when you try to integrate some functions. Now, the first example I have is 1 over x, but this is technically not right because it's not defined there at 0. So that's kind of a problem spot. Oh, discontinuous almost nowhere, which is a technical term. Oh, I see. Yeah, I hope I learn more about that later. I'm not going to go into full detail about these parts here. But yeah, 1 over x looks kind of like this. If this is 0, this is 1. This is the interval, more or less. Now, I said it's not actually defined at 0, but if you want to like think about it, this one is a really bad discontinuity. I'm not exactly sure why, but you can't Riemann integrate that. I mean, if you change this to like 0.5 to 1, you can totally do that. That's fine. And then this thing, I think it's usually called the indicator function. So for the rationals. So I'm going to put 0 as green and then 1 as red. So when x is rational, you get ones like these. There are a lot. There are too many. But at the same time, if x is irrational, they all just kind of stay at 0. So it's very messy. And so this is really bad. But this is not totally important for this. Now I want to give a few examples of discontinuities that are actually okay. So if your function has like a jump like that, that's cool. You can do that. Or if it's removable, if it's like like this. That's also okay. You can do that. You can Riemann integrate over that. If it's like the interval is like that, that's cool. Here. Yeah. And so I'm going to actually start by, I guess, defining the integral, but we're going to construct it. So motivate the definition by actually constructing a Riemann integral out of starting from a partition like this. So let f be a Riemann integrable function from the interval a, b to the real numbers. So this picture here is just the interval. And so what we're going to do first is going to partition the interval. So this is like cutting it up almost into a bunch of subintervals. So I'm not going to draw too many. Maybe I'll draw like this. I'll put some dots here because maybe there are more. So we'll let a be called x0, x1, x2. Maybe there are more. And then this is xn minus 2, xn minus 1. And then b is xn. So if you counted them, this is the first subinterval, second, third, all the way up to the n minus 1, and then the nth subinterval. So there are n of these things. And so we call the set of these subintervals P, and I put length in quotes because that's not something I really defined here, but just kind of go with it, I guess. And we call the length of the longest subinterval. So we want the longest subinterval because later we're going to shrink this longest subinterval down so that all the other subintervals that are going to be smaller than this biggest one also shrink with this one. So this is just convenient. So the length of the longest subinterval is called the norm or mesh of P, and it's just noted with like absolute value bars around P. Okay, so we'll consider the sum, but we can kind of interpret the sum graphically, where let's say n equals 4, because I'm lazy. I don't want to draw too many. So when you start this kind of stuff, like usually they draw pictures like with rectangles capturing the area under the curve. And this is kind of what I'm going at as well. So hopefully, yeah, if n equals 4, let's just draw 4 subintervals. These are very fat subintervals. We're going to shrink these down later. But I want to draw this. Maybe I'll draw it like this. More like this. And yes, they don't need to be the same length, these subintervals. They can be different lengths. Okay. So this is x0, x1, x2, x3, x4. And so in the sum, we have this f of ti, where I is in the subinterval. So we do this for every single one. So here, this is t1, because then this thing here is f of t1. Similarly, over here, this is t2. This is, I probably shouldn't put that. Yeah, f of t2. Over here, t3. Right, it doesn't really matter where these t's are. They're just in the subinterval. This is t4. So this is f of t3, f of t4, right? So the summation captures each of these areas. So when n is 4 for this example, this is a really convenient picture. Also, if the function goes negative, then the rectangle like flips itself and it becomes like a negative rectangle because it's signed area. I think I don't know if I said that. I'll say it later anyway. But yeah, it's a signed area of the rectangle. If these f's are negative, then they remain negative. Yeah. So here's when we make the sum capture the area under the curve better and better until it becomes perfect. So we're going to let n become arbitrarily large. So that means the number of subintervals becomes arbitrarily large, say infinitely large. And so this the interval AB gets cut into a lot of tiny pieces, and a lot of the times what'll happen is like they call, like later on they'll say like they'll call these subintervals like delta x's because they're just like really really tiny pieces. And so the length of each subinterval is going to shrink. And so this is kind of the same thing as saying that the norm of the partition goes to 0. So if the largest subinterval, the size of that shrinks to 0, then all of the other ones are also going to shrink to 0 because it's the largest one. So I've written here that the limit as n goes to infinity is like the same thing as writing the norm goes to 0. Lots of times I think you'll see both kinds of notations. So this limit on the sum, we say, is the definite integral from a to b. So that's this thing. Whereas the sum, the discrete sum is like these two. So here in the picture, at least I got this from a random textbook, they made the subintervals equal length. So I mean, you don't need that, but that's just for the sake of the picture. So yeah. Before I go on to this, no, I don't want to say anything. Okay, let's just go ahead. Okay, so there are 3 parts that I want to talk about. So if f is Riemann integrable, then we can call a function capital F of x as like the integral from a to x of f of t dt. So sometimes you'll see this t called a dummy variable. And that's because it doesn't really matter what letter you call it. I mean, I guess if you wanted to, you can also say this is x is a dummy variable, but this is just for demonstration. It's important that you keep them distinct. Like don't put the x inside, but also on the bound of the integral. Like don't do that. That's not good. So this capital F of x is this integral. I'll explain more what that actually can represent visually in a couple of slides. So this function is continuous. It just will be continuous. And then the second point is if the lowercase f is continuous at x, so this is like t equals x if you want to think about it like this, because we had f of t here, we can set like t equal to x, and if f is continuous at x, then you can actually differentiate the capital F there, which is nice. And that gets into the concepts of the antiderivative being used to evaluate the Riemann integral, which is this third part. So later, of course, I'll talk about, an antiderivative of f. So this third part, it just says you can use the antiderivatives to evaluate. Here's a definite integral. So here we have 2 constants in the bounds. Here, x is treated as a variable, so that's why we think of this as evaluating capital F at x, right? I hope that's not too confusing. Yeah, I already said all these things here. Okay. I'm getting parched. Okay. Any questions before we go on? Oh dear. I zoomed by like 15 minutes. Okay. Yeah, I severely overestimated the time I would take to do this. Okay, I guess no questions. So I'm not actually going to prove the first part where capital F is continuous, but I will say some things to hopefully, I guess, internalize this concept. So what actually is capital F of x if you want to think visually? We can think about it as the accumulation of the signed area under the graph of f from a to wherever x is. X should be at least in the interval a to b. So this is going to be a little difficult to draw. I've tried a few times, but it's not exactly how I want. There's a nice animation on Wikipedia for this, or maybe you can watch maybe some of like 3 Brown 1 Blues videos on calculus. He probably has a better animation for this, but I will attempt to draw what I mean. So if capital F is the integral from a to x, then we'll put x somewhere here. And then we can draw the area from a to x like this. So as we're drawing in the area, this we're going to call like, I guess, a. That's a value, that's an area. It has a number to it. And so we can go onto this graph here, which is for capital F of x. So on the left here, this f of t, and so x is in a and b. So then over here, we can put x in the same spot, because t and x are like the same. It's just the real numbers. So we'll put x there. And then, so the value of capital F of x at x is going to be a, but this is a. So as we draw in the area, you can imagine the curve going along like this. Or if you want to think in like the vertical axis, like just goes up like that as we move this way in capturing the area. So as we increase as we increase x, this blue area is going to increase, and so this value of a is going to go up along this curve. Yeah. So then, okay, so here at least, f is continuous. So that was a really convenient example, but we can also try with, a piecewise continuous function. So we'll start at a and continue to draw the area. And so here, this is a. Well, I probably shouldn't put a different color because I want this to continue. I don't want to. Yeah. So at least for the constant part, when we started drawing in the area, capital F would increase like that. So we move along the curve like this when we're going from A to C. And then if we go from C onwards, we had a change in how lowercase f behaves, but we can still go. So if we start from here, just add a little bit of area, notice that we only go up a little bit and we're still basically like really, really close. So if you think about like just adding like a really small sliver, it's not going to make capital F of x discontinuous. Like you'll still, you know, I hate to say this, like you'll still be able to draw the curve without lifting your pencil. Okay. We can continue like this. We can continue adding area. So if we continue drawing like this, because this part here is linear, we expect the area to increase differently. So it'll go up like probably this much. What is that, like around here? Yeah, more or less. It'll go up like that and we go along the curve like that. So that's the piecewise continuous example. And now I have nailed this in the head. A discontinuous. Oh dear. Did my thing stop? Why did it do that? Oh, I think my iPad disconnected from the internet. Whoa. Okay. Yeah, sorry. My iPad just, okay. Right, can you see that again? Does it still work? Okay, excellent. Sorry about that. Yeah, so this is the discontinuous case, but here at least this discontinuity is okay. This is still a Riemann integrable function. Yeah, she came in and asked me a question. Probably should have told her I was doing this. I'm back home, I'm not at the university today. Anyway. Yeah, so in the discontinuous case, we can again do the same thing. We can start at A and we can start accumulating area like this. And then of course, you go up like that. But then once we start with this part after the discontinuity, we can draw like maybe the small sliver. If you wanted to add that small sliver of area, it's not a huge contribution to the area. So we only go up a little bit. And of course, this means you're still basically there. Nothing really happened to capital F of x. It did not jump. But, you know, if you can see capital F of x, it looks like something weird is going on. Something, this spot looks kind of bad. I will talk about that later. So we can continue accumulating area, and of course, this thing will go up just much faster because there's just so much area here as compared to before. So you can think about these things. Yeah. Okay, so right, that's part one. Capital F of x is continuous. I hope this makes some sense. Maybe later I'll post the animations that I wanted to show. But yeah. So now this is the second part of the theorem. This is where I want to differentiate capital F wherever lowercase f is continuous. And this is kind of what I was getting at here, because here it's discontinuous and this thing looks like a corner. That's not good, but at least here it was piecewise continuous, but it seemed like, you know, kind of smooth there. That's pretty cool. So we're going to apply the limit definition of the derivative on capital F, and we see that we do this, and then remember capital F of x is equal to integral a to x f of t dt. So that's where I'm getting these two, because we're putting in x plus h and x into there, subtracting. And so here we're going to use an integral property, which I'm not going to prove, which is where, like, you can think about like negating this integral, flipping the bounds, and then because it's from x to a plus a to x plus h. You can put those together and it'll become the integral from x to x plus h. You probably already knew this. That's not too important, but this is the limit that we finally arrive at, and we need to show that it exists as equal to f of x whenever f is continuous at x. That's important. And so to do that, we are going to use kind of like a bounding argument. We're going to squeeze this limit, or rather, I guess, this integral, and then take the limit. But yeah. So, man. Okay. So here I've written some kind of interesting looking quantities, but I'm going to draw them out so you don't have to worry about knowing too much about what these mean. So infimum, they have specific definitions, but I don't want to get into them here. We can call this the greatest lower bound. This thing is the least upper bound. Don't worry too much about this. I'll tell you what these basically are, more or less. They're just defined like that to, I guess, at least what I think is to cover many cases. Because obviously, well, first I'll explain what these are graphically. So, okay, so I'll put like x in the middle of this diagram in this thing. So we'll make an interval x minus h, x plus h, and here I've kind of like implicitly assumed that like h is positive. This is just for convenience, and that's why, I mean, you can have h negative, but that's why we have the absolute value bars here. But for the sake of this explanation, don't worry too much about that. So we have x here, and then we have basically this neighborhood around x, where we have this interval. It's like x minus h to x plus h. X is right in the middle. And so we can consider basically like, make this blue, make this m. We can consider basically bounding. That's why I have this asterisk here. Bounding f above and below by capital M and lowercase m, which is that blue and the red. So in this interval, we want to find basically like the tallest value that f takes on. I mean, in this picture I made it like continuous, but there are a lot of other interesting cases where the actual proper definition comes into play. But think about it as like the maximum value, but it's a little different. So if you can see from the picture, then this point here is capital M. So that's like there. And then you can look down here. This is lowercase m. This is like the lower bound. So you can see that the f of t is kind of in between, always, at least in this interval. I mean, if you look behind the x minus h, it goes above. But we're only worried about the interval x minus h to x plus h. And so we have this capital M and this lowercase m to kind of bound them above and below. So we're going to work with this, and it'll become useful later. Yeah. So this is where the continuity of f is important, because this lowercase m and this uppercase m, we want them to converge to f of x when we shrink the h. So I'll just draw this out here. So in two examples. So for the first case, we've got this okay discontinuity Like it's still Riemann integral there, but like it's still not continuous, and that's the problem. So this is x plus h, x minus h. I'm making them a little smaller just to emphasize that we want to shrink them. So of course, when you see in this picture, the lowercase m is like here, and then the uppercase m somewhere over here. And so when we shrink this interval, like when we bring these two, like for visualization, when you collapse them, then you can imagine the uppercase m going here and lowercase m moving there, right? But the problem is this is f of t. This is not the same thing. M went to here, and little m went to here. They did not converge. However, when f is continuous, so I'll draw it again over here. Let me put a big X here. This is fail. This when f is continuous at x, so here, then we can do the same thing. We can do x minus h, x plus h. And you can draw little m is over here. Of course, this corresponds to a value here, but for the sake of the picture, this is how I'm going to draw it. So that's capital M, and then f of t is here, or f of x is here. I might have said f of t here. I meant f of x. So then when we make this interval very small by reducing h to 0, not reducing, taking the limit as h goes to 0, this capital M will go this way, this lowercase m will go that way, and so they both become very, very close. They approach and converge to f of x. And that's important because we're going to use that in the bounding argument to come. And yeah, I've written that explicitly here. This is basically what I did, but just written out. The limit as h goes to 0 of little m goes to f of x, and the limit as h goes to 0 of capital M goes to f of x. Same thing. Okay, so here, okay, so we're using another property of integrals here that I didn't explain. If like a man, yeah, sure. If a less than or equal to b less than or equal to c, then integral a less than or equal to integral b. That I did not prove, but that's what I use here to get to this inequality. Because we know that the capital M will always be bigger than f of x, and then the lowercase m will always be less than f of x. And so that's kind of the inequality we have here. And then of course I just put the integrals, I just integrated them. Right, yeah, I said that here. Why did I? Yeah, okay. So to visualize this inequality, I'm going to draw each of these out, more or less. So we'll start by putting x here. Of course, this is a very convenient curve. Then x plus h, and then x minus h. And so again, we want to find capital M, which is like here, and then lowercase m, which is here. And so let me, that's not the right color. I'm going to draw lines above and below for the visualization. So this first integral is the integral from x to x plus h of lowercase m dt. So this captures the area under m, this red line, from x to x plus h. So that's this red area. This red rectangle is m. Similarly, this last integral on the right, we do the same thing. Capital M, integrate from x to x plus h. So we have this. So it's like a little bit of a taller rectangle. And then finally, we have the integral of f of t from x to x plus h. But this integral represents the area under the curve, so perfectly captured. So it's this thing here. Oh dear, that was not. Maybe I'll draw it like this. Yeah, I hope. Man, that's not that good, but I hope that makes sense. So the big blue rectangle is bigger than the green area, but the green area is still bigger than the red area. And that's what this inequality visually looks like. But these are rectangles, and so we can kind of write them a little nicely. Like we can actually come up with nicer looking values for these two in the next slide. So this next inequality is just found by multiplying through by 1 over h, because remember, h is not 0. We let it tend to 0, but it's not 0, so this is okay. We can multiply through by 1 over h on all of these integrals. This still holds. If h is negative, then stuff flips, but don't worry about that. And since m is constant with respect to t, that's kind of what I was getting at earlier with, drawing this line. It's a constant. It's just we find it depending on the value of x. Basically, oh, I forgot a dt. Okay, yeah. We can interpret it as an area, and so this becomes 1 over h times m of, or lowercase m, and then here, of course, the length of this is x plus h minus x equals to h. That's what we're doing here. That's the length of that part of the subinterval. The interval. So that's just h. And so these things cancel. And so we just get lowercase m. The same thing is for the uppercase m. And that's just how we're integrating these two. So really, this is just m. This is also just capital M, is what I'm getting at. You can see from the picture, this is h, and this is m in terms of lengths. And then this is lowercase m, and this is h. Then the integral is the area, so then it's mh for both of them. And then you divide it by h, and it's just back to m again. Yeah, so then, right, this is I just replaced these two with lowercase and uppercase m. And so when f is continuous x, we said that the lowercase m and the uppercase m, they converge to f of x as h tends to 0. So this is why the continuity part is what we want. So we can take the limit as h tends to 0 for each of these parts. And this is like, I think people call this like the squeeze theorem. So that's what we're using here. So we're taking the limit as h goes to 0 of all three of these quantities in the inequality. And so this thing goes there, this thing goes there, because we said that. But remember that this limit was actually the limit that we saw earlier. I want to go back, but I don't want to like give you guys too much of an eyesore, so I'm going to go back a little slowly. This is that limit. This is the derivative of capital F with respect to x. So that limit is what we just bounded and showed by use of the squeeze theorem. Oh, not drawn. This arrow goes. This one goes here. Yeah. So because it's squeezed above and below, and this is the inequality squeeze theorem, we can conclude that the derivative of capital F with respect to x is equal to f of x when f is continuous at x. Yeah. Okay, so that's part 2. Now part 3 is the last part, and this is the familiar part, but this one I won't have a lot of pictures to draw. But we'll still go through this. 10:41. Okay, I'm good with time. Okay, so let's remember what part 3 said. Part 3 said that if capital G is an antiderivative of f, then we can use the antiderivative to evaluate the integral. And so here we're actually going to say what an antiderivative is. An antiderivative is just something when differentiated spits out, what you want, lowercase f at x. And so we want this to be true on this interval. And so you should think about later when functions have antiderivatives. So I'll leave that to you guys. So that's what an antiderivative is. And so we're going to say that antiderivatives differ from, I call this indefinite because we have a variable x in the upper bound as opposed to having 2 constants. It's just weird terminology. Don't worry too much about what I mean there. But the g of x differs from this integral by a constant c. And so later you can think about, like after we did this, you can differentiate both sides, and this g of x when differentiated will go back to f of x, and then we already showed earlier that if you differentiate this integral with respect to x, you'll just get f of x again. So that's nice. And then this c, when you differentiate constant, you get 0. So pretty cool. So to prove this part, which we'll use to establish the final result, we're going to partition the interval from a to x, right? And so a to x is, let me draw like a, x, b. This is only part of it, remember, because x is in that interval. I'm going to do, only going to do this part. So that's x0, and then all of these things, xn. Doesn't matter how many. You get the point. So we've cut it up into a bunch of subintervals. And so we're going to consider this quantity. This looks very similar to like when you've computed like the average rate of change. I guess this is like if you just put the limit as xk approaches xk minus 1 or whatever, you could get like the derivative. But right, we're just looking at just like an average. And so we use the mean value theorem to show that this above quantity is equal to g, g prime of tk. But remember, g prime is equal to f of tk because, right, we established that earlier, definition of antiderivative. And so we have a tk, which is guaranteed by the mean value theorem, to lie in this interval. And so this is, we can always have this tk in the subinterval, whichever subinterval it is. This is true no matter how small the subinterval is. And we're going to use that. to get the leverage we want. And so we have this equality here when we multiply through by xk minus 1, because right, this is not 0. It's good. So then this equality is just for just any subinterval xk minus 1. Remember, we had the partition from x0 to xn, from a to x. We're going to consider this quantity for every single. Whoa. Just said my internet connection was unstable. Okay. Can you guys still see this? Yeah. Okay. Yeah. So what we're going to do is, since we have all of these, we can consider all of the g of xk minus g of xk minus 1 for all of the subintervals in the partition that we made. We can actually sum all of these values up, and they'll still be equal. So we have this sum of f of t sub k times xk minus 1 is equal to sum of g of xk minus g of xk minus 1. And we're going to go sum through all of the subintervals in the partition. And so we're going to expand this sum like so. So we do the k equals 1, k equals 2, all the way k equals n. And so notice that you can cancel a lot of these terms out. This is called telescoping. We can get rid of this term, because see, this is g and this is minus g. And we can do the same with this. And then I put dots here, but you can imagine that this g of x sub 3 is going to get canceled somewhere down the line there. Similarly, this g minus g of x to the n minus 2 is going to be canceled somewhere behind it. And then this thing gets canceled here. So what we're left with is this and this. This goes here, this goes here. So this is just g of xn minus g of x0. But we already said when we did the partition that xn is equal to x and x0 is equal to a, because we started partitioning from a and then we went all the way to x, right? But then I said that all of these quantities, this equality for these quantities, this holds regardless of the size of the subinterval. So I can shrink the subinterval, all of the subintervals, as much as I like. So I will take the limit as n goes to infinity. So remember before, this is like the same thing as norm of p goes to 0. So the biggest subinterval, whatever it is, I'll shrink that to 0. So we have a infinitely many subintervals, each one size going to 0. And then we do the same thing on the other side of the equality for the g of xk minus g of xk minus 1. We take the limit as that, n goes to infinity. But because this equality holds regardless, this thing is not going to change. It doesn't. This thing doesn't really depend on n, because that was just an arbitrary cutting, like of the arbitrary partition of the interval. Like even if n was like a really, really big number, we could still do the same telescoping thing we did here, and we would still just get the same thing. So notice that the left side of this equation is just the Riemann integral definition of the integral from a to x of f of t, and then the right-hand side is unchanged. So then this is the final equality that we get. So then, right, we move the g of a over to the left-hand side. A is a constant, g is just a function. So this thing is constant. So that's what we get. So this is the plus c that we wanted. So when you're doing indefinite integrals, and they always say remember the plus c, this is where we're getting that. Okay. I probably should have put this line after because I said it was from G of B to G of A, or G of B minus G of A. So when we evaluate G of X at B, we get the integral from A to B. And you can get this from the previous equation. This is the familiar formula. This is nice. I think that's it. Do I get to do this? I don't know. That's for later. Do it when you actually learn the proof. This is just something I wanted to say. Yeah. Anyone have questions? No? It's okay. Yeah. I left in an extra slide in case I wanted to write something down. I think all I want to say is like, this is not like the only kind of like fundamental theorem of calculus. There are a handful of theorems from later courses that you'll take that are very similar and in fact basically the same in a lot of ways. So if you've seen some of these, I'll write some equations down. F of B minus f of A, where B and A are the terminal. And then similar, that's in like the multivariable case when you're doing like a path integral. So instead of just over the real line, you can get a similar result when you're doing a integral over some curve in space with terminal endpoints B and A. And then it's like also similar to one in the complex plane. F of z dz when f is analytic over c, then equals like, again, f of b minus f of a, where b and a are just the terminal points of the curve in the complex plane. So yeah, those are just some. And then there's like Stokes's theorem, which is like a really crazy version, like a kind of fundamental theorem of calculus proof, which is like from differential geometry. But they're all saying very similar things, and they're all very related. So this is only the beginning. Yeah, so that's all I wanted to say. Thank you for coming to my talk. I'll see you later. I think I'm done.